Welcome everyone to our afternoon session. Already we had some fantastic talks this morning, and I'm truly excited to present to you our next speaker. He's a professor of statistical learning at Oxford University. He's a senior research scientist at DeepMind. This is Professor Arnaud Doucet, and we're very pleased to have him here with us. And Arnaud is going to speak about a very hot topic these days, generative modeling. And the title of his talk is From Denoising Diffusion Models to Diffusion Schrodinger Bridges. Arnaud, the floor is yours.
Thank you for the invitation. So I'm very happy to be here. I haven't been to the Turing for at least 4 years, so it's good to be back. So I'm going to talk about some of the work we did over the past now 2-3 years on this class of generative modeling techniques. I've worked with many people on this topic. So it's bad to single out people, but I will still single out a couple of people who've been particularly basically instrumental for this work to happen. In particular, Valentin de Bortoli, who will be talking later in this session, and also James Thornton, who was my PhD student. And we started working on that actually now over 2.5 years ago. Okay, so really fantastic area. So I tried to convey actually this excitement during my talk. So I will first start by introducing this kind of denoising diffusion model. So I know some of you are already familiar with this topic, so bear with me, which hopefully you'll find more interesting. Okay, so let's start with basically some kind of introduction to generative modeling. Okay, so literally it's all started, in the mid 2010, maybe people start in machine learning to kind of like work on this kind of generative modeling, and they were like VAEs and autoregressive model, and in particular GANs were introduced, which became actually extremely influential. So the GAN paper by Goodfellow has over like 40,000 citations at least. Okay, so it was very good, very interesting. And what's the goal of generative modeling? Where I always think of the image basically kind of a domain where you've given an empirical a database of images, and you want to generate new images that are basically look like the one you have in the database, but are not carbon copy of it. Okay, and you might be interested in doing that also for protein, for music, for text. And why you want to do that? Well, for example, it's not because you're interested in generating fake image per se, although it has an application, but typically because you're going to use this kind of generative model as some kind of data-driven prior, a kind of clever data-driven prior. Okay, so for example, if you want to do some kind of image reconstruction, well, in the good old days, when I was actually a PhD student, you would set some kind of Markov random field as a prior basically on the image, and we'd basically combine that with the likelihood and do some kind of empty sampling. In a sense, okay, that could work so. But when you think of it, the problem also with Markov random field is that you can simulate Markov random field, and it's never going to look like the natural image you're trying to reconstruct. So this is actually essentially pretty poor prior. So these kind of things, I think of me as a kind of originally raised as a Bayesian, that this is generative model is kind of like a way to obtain from data very good data-driven prior distribution. Okay, so all this area, basically generative modeling, GAN were, I think, prominent basically till 2020, and then there was basically the denoising diffusion model. Actually, they had been proposed in 2015, but people hadn't picked it up because there were actually quite a lot of tricks missing to make it work. So it's really the kind of 2 papers by Jonathan Oh in Berkeley on Yang Song in Stanford that kind of really had a massive influence in this domain. Okay, so ever since, this method has been widely used. So they are basically at the core of daily 2 image gen on stable diffusion. Okay, and there's like now we have Midjourney. There are many more. Every week there's a new kind of system that uses the denoising diffusion model either to produce image or protein or music. It's a kind of very exciting area. Okay. So why people got excited? Well, there were 2 reasons you got excited. There was this paper by OpenAI, them again, that shows that, well, you use this kind of model and it beats GAN in terms of like perceptual metrics like FID. Okay, so that was a kind of like influential paper. They say, well, maybe you should forget about GAN because this thing actually is doing better. On this kind of state-of-the-art performance, they've been repeated not only in the image domain, but also for music, protein, audio, and so on and so forth. Okay. So the other thing also that people found attractive compared to GAN is that there's not this kind of adversarial training. So it's typically actually much more stable to train than all this kind of GAN type algorithm. Okay, so the cost to pay for that, and we'll see later, is a little bit slower to basically do to generate synthetic sample using denoising diffusion than it is to using GAN. Okay, so what I'll do now, I will introduce how this kind of techniques work. Okay. All right, so the idea is going to be the following thing. So remember that what you've been given is basically, say, think of it in the image domain, a collection of images. Okay, that define an empirical distribution. It's going to be the distribution of the data. And now you want to generate new sample from this distribution. Okay, so what you're going to do essentially is going to take your data distribution. Okay, and you're going to progressively transform this empirical data distribution to a Gaussian distribution. Okay, so if you look at a kind of basically a sample level, it's like you pick one sample from your basically database, and what you're doing, we're just going to add progressively some noise. Okay, so that essentially after a few iterations, you're going to have some kind of Gaussian noise sample. Okay, so that's the idea. So this is a noising process. Okay, and then we'll see obviously the denoising process, which is obviously much more exciting than adding noise to your data. Okay, so mathematically, it's like probability 101. You simulate basically a Markov chain at the kind of distribution level. So you have sample from peanut. It's going to be empirical data distribution. Okay, I'm going to assume it has a density here, but okay. So that's the true data distribution, let's say. And you add noise, so you're going to have this transition kernel. Let's specify them a bit later. Okay, so this is the joint distribution of this kind of Markov chain you generated. Okay. And I'm going to denote by pk xk the marginal distribution of xk under this forward noising mechanism. Okay. So now what I want to do, so this is forward noising. Now I want to do denoising. So what is denoising is going to be to say, well, okay, what I want to do, I want to sample from peanut x naught. Okay, so I want to generate new samples. So I'm going to do something a bit convoluted. I'm going to basically write the joint distribution of this forward Markov chain. I'm going to write it in the backward direction. So I start from the final time marginal, okay, and basically have this product of this kind of backward Markov transition kernel. On this backward Markov transition kernel, in the forward direction, you add noise progressively. So the backward Markov transition kernel corresponds to denoising operation. Okay, so that's basically it. So if you could do that, well, obviously, what you would do, you would sample final time n some noise sample, because it's really roughly Gaussian. You would basically recurse backward till time 0, and you would have a sample from peanut. So that's the high-level idea of this denoising diffusion model. Okay, so now be a bit more specific. Okay, so I'll say typically peanut, think of it as the distribution of the data, the initial distribution of the noising basically process. And it is, we want some transition that add noise progressively, but such that basically after a few time steps, you have like almost a Gaussian noise sample. So what you do nothing fancy, you're going to use some simple autoregressive Gaussian. Okay, you pull as a forward noising process, an autoregressive process, and obviously, when alpha is strictly inferior to 1, say 0.99, say you add noise just progressively, then you know that essentially the marginal distribution is roughly Gaussian. Okay, so what you're going to do, you're going to mimic in ancestral sampling, you're going to say, okay, the ancestral sampling procedure in practice, if I wanted to implement exactly this procedure, I would sample from the kind of corrupted data distribution under this forward noising mechanism, but I don't need to bother because I know that anyway, this thing is roughly Gaussian. So I sample from Gaussian, and I still need to sample from this kind of, kind of backward Markov transition kernel, which corresponds to some kind of denoising mechanism. So that's going to be the hard bit, okay? Okay, so how are we going to do that? I said that there's nothing complicated about it. Okay, so you're going to go. So remember that this is what we are using. This is a kind of forward noisy mechanism. It can be much more general, but let's stuck with that to start with. And you can just also add noise. Okay? You could just have xk plus 1 is xk plus some kind of essentially Gaussian noise increment. Okay. Okay. So now you say, well, what I need to approximate now this backward Markov transition kernel, this reverse transition kernel, which has the stuff that takes me from xk plus 1 to xk. So I need to denoise a bit, basically, the sample xk plus 1 to go at time xk. Okay. So now, well, what do you do? This backward Markov transition kernel, you apply base rule. So you apply base rule. So this is essentially prior pkxk time forward transition kernel that takes me from xk to xk plus 1 divided by marginal distribution, obviously, of pk plus 1 of xk plus 1. Okay. So now I want to approximate that. Okay. I'm going to do things a bit dirty here. I could say, okay. Anyway, I can drop, I write proportional, I drop xk plus 1 because pk plus 1, xk plus 1 is a constant. Okay, and now I do say, okay, I'm going to approximate that by some kind of Taylor expansion around xk plus 1. Because, you know, with high probability, xk and xk plus 1 are very close to each other because just add noise very progressively. Okay, so this is what you do. So there's an approximation here, just Taylor expansion. Okay, and now remember that this thing here is basically some kind of simple linear Gaussian kernel. You have the simple term here, you recombine that, everything, and you have that basically this Markov transition kernel is a Gaussian, also it can be approximated by a Gaussian distribution of argument xk, mean that is given by this expression plus a variance term. Okay, that's all I've done. So Taylor expansion, nothing else. Okay, no, I'm not completely done because if I want to sample that, well, I need to know the score. So what is this score here? So it's a Stein score. This is derivative with respect to x, and there's no, doing statistics here. There's no parameter theta. There's no Fisher score. Okay, so contrary to what one of my reviewers said recently in the journal, the famous statistical journal. Okay, so we have it. So we're here, and now we need to approximate this guy. Okay, so what we're going to use here, we're going to leverage the fact that pk plus 1, if you take any score at time k, the gradient log pk, the marginal distribution of sk under the forward dynamic, well, you can rewrite it as the original data distribution to which you apply this kind of noisy mechanism, which is basically where you have the noise from x0 to x1, x1 to x2, x2 to etc. till xk. Now, because I have a very, very simple forward dynamic, okay, then I can write explicitly this transition kernel. It's obviously a Gaussian of argument xk, means which is going to be, say, beta x0 plus some kind of some variance term. Okay, so that we know this expression. And now you differentiate on both terms. Okay, you take the gradient of the log, and you get this expression here. Okay, so here we get that basically the score of interest is basically the expectation with respect to the conditional distribution of x0 given xk of a term, an integrand here, which is known. Because this expression, the gradient of the log forward transition is trivial stuff. Okay, so this is a conditional expectation. We are not yet done because, well, I don't know what is this distribution. And you cannot even do MCMC if you want because you don't have access to a normalized version of that. You just have sample from P0. So you need to do something else. Well, it's conditional expectation. If you have a conditional expectation, you want to approximate it. Well, what you do regression. Okay, so we're going to do regression. And we're going to say, okay, what I'm going to do, I'm going to basically parameterize a class of function. It's going to be a neural network, okay? And I'm going to minimize basically the square norm, the difference between this function and basically grad log of the transition. Okay, so if I were looking, and here the expectation is related to the joint distribution of x0 and xk, which is very easy to sample. Okay. Okay. So by basically property of the conditional expectation, if you could look at all essentially function that minimize this guy, well, you would have actually the conditional expectation. Okay. So obviously, practice, you don't have all the functions, so you parameterize, I said, that period the neural net, and basically you're going to minimize this expectation over the parameter of the neural net. Okay, so that's the thing. And you can do stochastic gradient for that because I say you can sample easily from this distribution. Okay, practice, you need to approximate the score not only at given time k, but all the intermediate time step. So what you're going to do, you're not going to learn a different, neural net at each time step. It'd be too computationally expensive, and also the scores are very close one to each other. okay, when the K varies by just 1 or 2. So what you're going to do actually is you parameterize, you consider neural nets going to parameterize by time and space, and basically you minimize this loss. Okay, so you sum all the loss and you learn your neural net with that. Okay, so that's very easy because you can mini batch over the time. Okay, the time horizon, which is important because n could be quite large. And you can also have unbiased gradient of this guy on this gradient. So unbiased estimate, sorry, of this expectation and of its gradient, the gradient of this loss. Okay, so that's basically what you've done. When you've done that, you have essentially an estimate of the score at all the intermediate time step. And now what you're going to do is basically eventually run your approximate ancestral sampling mechanism. Remember what it is? You start at time n, you sample from a Gaussian, and then basically you sample now from this kind of backward Markov transition kernel, reverse transition, which basically take you from xk plus 1 to xk in the score. And this thing is basically you do that till time 0, and at time 0 you have a sample. Okay, so that's basically what you're doing. Okay. So why we call that diffusion? I mean, obviously, for some people know diffusion much better than me in this room. I know a few here, but obviously, because if you look at what's going on when you like increase n basically to infinity or fixed time interval, you're going to get that really what I've written before, which is autoregressive Gaussian, is simply basically the time discretization of the Einstein-Uhlenbeck process that has been initialized at the distribution of the data. Okay. So this is what it is. On what is ancestral sampling, where you can think is like you look at the time reversal of this process. On the time reversal of this process, it's well known from the probability literature. It's all resolved by Anderson and Haussmann and Pardue that basically it satisfies this SDE as well. Okay, so here I'm not working with a negative Brownian increment. I don't like that, negative time. So I just basically white is just like X capital T minus T. So it initialized this reverse time diffusion at the final time marginal of the forward diffusion, PT, which is intractable. And then basically you have the score that pops up without doing some dirty Taylor expansion. Okay, so this is it. Okay, so that this thing is the exact, if you want, time reversal of this noising diffusion. And we make two approximations. Somehow when we implement these kind of things, we replace PT by some Gaussian noise because we know it's roughly the same. And we approximate this score by some neural net. Okay. And what we can show is actually how could you learn, if you think of it in continuous time, you're more comfortable thinking in terms of continuous time. All the parameter of this neural net, you know, remember I had basically established the loss. You know, I had basically done it by hand, but it turns out that really what you could do is that if you minimize the Kullback-Leibler discrepancy between this pass measure and this pass measure, and you minimize that with respect to theta, you end up having to minimize this loss, which is literally exactly the continuous time version of the loss I had written before. So basically, it's just a KL minimization problem. Okay, that's what it does. Okay, so that's nice. So there's been a lot of results that have been proposed in the literature. So I'm not going to discuss them because basically Valentin is going to do it better than me later. And this result is due to Valentin as well, to start with. So we should give him complete credit. But one thing which is important is like, if you look at this algorithm, okay, you look at this kind of diffusion, and this is what you simulate in practice. Okay, so okay, it's a non-homogeneous diffusion, finite time interval, and you could say, okay, it looks like Langevin somehow, and you do some kind of sampling in super high dimension. If you spend your life doing MCMC, you're like, this is never going to make. How can it work in in high dimension? This kind of algorithm, it's a kind of bit puzzling actually. It's on. You observe that practically it's fine. It's completely actually generate image which are extremely diverse, even if the kind of initial random seed are very not too far from each other. So one thing which is remarkable is actually what you can show is that essentially because you approximate this reverse time diffusion, but the reverse time diffusion, it inherits the mixing property of the forward diffusion, which are basically an Einstein-Uhlenbeck process. That's why I think it's actually quite nice. Okay, so when you try to bound, say, the total variation norm between basically the true distribution of the data on the law, basically what you simulated using the kind of approximate, essentially time discretized reverse time diffusion, then you can have bonds of the form which one bond corresponds to the mixing, okay? And you see this bond is behaving extremely well with T, but then you have this core approximation error on which there's been a lot of work recently. In the original paper with Valentin, it was a bit crude, exploding, but now people have made much progress, and I'll let Valentin elaborate on that. Okay, so that's basically some of the results, some of the things you can do with that. Yeah.
The mixing property on the reverse process is when the score is the right one.
Yes, yes. So that would be of the, you decompose the error on like basically the true kind of reverse time diffusion, initialize at Gaussian instead of PT. So the mixing of that on, plus then obviously there's a term appearing where you have to bound essentially the difference between the approximate time reversal on the true time reversal, which is the complicated bit, that's quite, but yeah. Okay, so you can do a lot of extension of that. So we originally, those kind of denoising diffusion model, they were done for basically RD, diffusion in RD. But you can do it for on a Riemannian manifold, for example. Particularly, it's been useful. It has been used quite a bit to do protein generation. So Valentin, actually, on Émile Mathieu, another PhD student at the time in Oxford, who is now in Cambridge, has been working, for example, with a Watson group in University of Washington, and they developed this actually superb system for protein generation, actually. Okay, so you can do that. And if you do that, well, how do you extend this? If you want to work on Riemannian manifold, well, okay. So, you know, before we had the Arndt-Schallenberg process. So you look at the Brownian motion on manifold, okay. Then you need to establish the time reversal when you basically look at what's happening on manifold, okay. It turns out it's feasible. Then you need to approximate the SD. So use this kind of framework of geodesic random walk. And you also, it's a bit complicated. So essentially, also for the score matching, this kind of the way we learn the score, some of the tricks don't basically, cannot be extended directly because you do not have access to the exact transition from time 0 to time t, contrary to what I was presenting in the RD case. So you need to use overloss to learn the score. You can use implicit score matching or things like that. But I mean, basically, it's feasible. Another thing we looked at was also how do you use that for discrete set space? So why is it important to do it for discrete set space? Well, okay, maybe first, when you think of images, it's not really in RD because the pixels are basically, you have level RGB and everything is set between 0 and 255. So, you know, that's one thing that it might be interesting to consider the kind of discrete thing. For music, so we have example in music generation in our paper on, obviously, importantly, on text. Could we do some kind of denoising diffusion model for this kind of text? Okay, so we have a paper doing that. And in this case, so you work really on this kind of now typically huge dimensional discrete space. What we done where is simply is you replace this kind of like essentially Arndt-Schallenberg by the Markov jump process that converges towards the uniform distribution. Okay, that's what we did. You can do time reversal for Markov jump process. So you can play the same game. So in this case is not the score that appears. You're not, so you have to learn some kind of ratio. You can do it as well by maximizing some kind of, minimizing some kind of Kullback-Leibler discrepancy, which is equivalent to actually obviously maximizing a continuous time evidence lower bound. What is nice about kind of thinking of the discrete, the kind of continuous time framework to do this kind of denoising in discrete state space is that then you have to simulate, when you try to simulate basically this kind of high dimensional continuous time discrete state space Markov chain, you can leverage the techniques that have been developed in chemical physics to speed up simulation. So we use in particular toe leaping, which is a kind of technique that have been developed to simulate biochemical networks. So you can accelerate simulation by using tricks that have been developed in other literature. Okay. Okay, so that's good. So that's the kind of denoising the diffusion so far. And now we're going to look at another problem, which is really the fact that those denoising diffusion, they take time. Actually, they're a bit long to basically simulate. Okay, so basically what you do, remember in the forward process, you need to noise progressively, slowly, okay, and then you learn to kind of denoise sample. But because it's basically you're going to have to do that progressively, you're going to have to simulate some kind of reverse time, discretized reverse time SD of a long time horizon. So it's kind of complicated because each time you need to have a new sample, you need to simulate this long basically SDA. So it's a bit expensive. Okay. That's it's not quite true. For those of you who follow the literature, there's been a lot of acceleration methods that have been proposed ever since we developed this paper. But basically, that was the rationale for what we've been doing. Okay, so I give you an example here. So assume you have an example where this is a 2D distribution. Okay, two-dimensional distribution. You diffuse forward, but you don't diffuse forward enough so that your sample is not a big blob like a Gaussian. You haven't diffused enough, basically. You should have diffused much longer to have a Gaussian. Obviously, even if you were able to learn exactly the score of this diffusion, if you initialize basically this thing at a Gaussian, it's never going to go to the data distribution because you really, there's a key assumption in what you're doing with the denoising diffusion model is that you diffuse enough that basically the distribution at time to the marginal distribution is roughly Gaussian. Okay. So could we do something to kind of essentially address this problem? Okay. So the first thing we're going to say is that, okay, couldn't we think actually of the kind of generative modeling problem as a kind of transport problem? Because this is really what it is. So in the forward process, it takes you from data distribution to Gaussian distribution. It transports basically this data distribution to the Gaussian distribution. And literally, well, the denoising process is the reverse thing. You transport Gaussian distribution to data distribution, and this is your generative modeling. Okay. And you think of it, when you think at the transport level, what we are doing is not super clever. It's not super clever because at the transport level, really, you think that essentially the transport you have between the data distribution, the coupling you have between the data distribution and the Gaussian distribution is basically independent. It's an independent coupling. You diffuse long enough to completely forget where you were coming from. And basically, you have the Gaussian distribution. This is a bit strange, actually. Okay, you can do it, it works, but it's perhaps not the best thing you could do. Okay, so what we're going to do here is the following. So we're going to get back to discrete time for the timing, and I'll move to continuous time later. So I'm going to get back to my what I call best process, but this is really the noising, the joint distribution of the noising. So this thing, distribution of the data, time transition, product of transition kernel of the forward noising process, the forward noising operator. Okay, I'm going to say I'm interested in finding the distribution pi on path space, which has, so I want to minimize the Kullback-Leibler discrepancy between pi and p, subject to two constraints. I want the marginal distribution at pi naught to be the distribution of the data, and I want the marginal distribution of pi at time n to be exactly the Gaussian distribution. Okay, so I want to resolve this problem. Okay, so this is known in the literature as this is a special instance of the so-called Schrodinger Bridges problem. And if I could solve this problem and identify pi star, the Schrodinger bridge, okay, then I could use this Schrodinger bridge so as to do generative modeling, because the only thing I would have to do is sample basically from the time reversal of pi star. I know that at time n is Gaussian. Okay, so there's no approximation that PT is approximately Gaussian. And then I recurse backward, and I would obtain at time 0, where a distribution which corresponds to the distribution of data by construction. Okay, so that if I could do that, it'd be great. Okay. Okay, so now just a bit trying to link that to what people are doing in optimal transport. So first, it's easy to see that the solution of this dynamic, essentially Schrodinger Bridges problem, dynamic in the sense that basically I'm not looking at the solution like a static transport. You just look at x0, x1, and you just look basically here over the whole path. Well, the solution of this dynamic Schrodinger Bridges problem is basically given by, it's going to be a static problem between just the initial and final time marginal. On this basically here, there's going to be the conditional distribution of the forward reference process, okay, So this is obvious. If you do that by KL decomposition, it's completely trivial that this is the solution. Okay, now this thing, what it is this distribution only of a two variable, x0 and xn, which minimize basically this expression. So just rewrite the KL decomposition here, decompose it of x0, xn on the rest. And you can rewrite that, okay? It looks like that, where here, this is the entropy actually of basically this distribution. And in particular, if the transition you've been using to add noise is not autoregressive Gaussian, but it's a simple, some kind of Brownian motion, well, what it corresponds to is an entropy-regularized version of optimal transport. Okay? So the only thing I've done here is I've leveraged the fact that this thing, well, if it is Gaussian, I can rearrange the term, and I find that basically what you're actually doing is that if you were minimizing that is the standard optimal transport with Wasserstein to metric, and now we have some kind of entropy-regularized, essentially, optimal transport problem. Okay, so if you solve this type of problem with some kind of Brownian noise dynamic, this is what you end up doing. You're solving an optimal transport problem on a regularized optimal transport problem. Okay, so that's all nice, this thing, but how do you solve that? Yeah, that's an important thing. People have been working on that forever. So it turns out that the person who first looked at that, so I think the algorithm was suggested by Schrodinger in his original paper in Schrodinger Bridges in 1932. But the person who actually analyzed this algorithm first is Robert Forte in 1940, who happens to be my academic great-grandfather, actually. I'm very proud of that. I didn't know before. Okay, so what it does, it's a kind of an algorithm that's been rediscovered 20 times in the literature, is iterative proportional fitting, also known for discrete measure as the Sinkhorn algorithm. So the algorithm has a long history, is permanently reinvented by, in various literature. And it proceeds as follows. You start, so you iterative algorithm, you start with a pi naught, your initial guess for the Schrodinger bridge, you put that to the kind of like essentially reference distribution, noising distribution. And then you alternate trying to minimize the KL between your current estimate of Schrodinger bridge on pi, subject to having the final time marginal, which is the Gaussian. And then on even iteration, you minimize again the KL, this time also with respect to the current Schrodinger bridge estimate, but this time you enforce the constraint that at time 0 you want to have the distribution of the data. Okay, so this is the original problem has two constraints. Okay, pi naught at time 1 you have this constraint. Sorry, at time 0 you have this constraint, at time n you have this constraint, and now you just enforce them only one at a time on you iterate. Okay, so this algorithm is well known. There's a long history for that. That it converged toward the solution of Schrodinger bridge on the small assumption. Okay, now let's have a look at what it does. Let's have a look at the first iteration of IPF. The first iteration of IPF, if you minimize the Kullback level discrepancy between pi and p, because at iteration 0, the first guess is p, subject to basically now you want to find that you want to enforce that the final time marginal is the Gaussian distribution. You write that, and what you find that basically the solution to this IPF stuff is basically pick, initialize, start from a Gaussian, on time reverse the dynamic of the forward process. But it's exactly what denoising diffusion model do. Okay? But the thing is that in denoising diffusion model, when PT, the marginal distribution of Xn under the forward dynamic is roughly equal to PRF, you don't need to iterate. You solve your problem right away. But if you were in a situation where the marginal distribution under the noising dynamic PT is quite far from the Gaussian, it means that basically IPF is not converging in one iteration, you keep iterating. Okay? So in continuous time, okay, so yeah, I'm not going to spare you, but on continuous time, basically it's going to mean that you're going to have to alternate. So on odd iteration, essentially, you have reverse time SDE, okay, which are initialized at the Gaussian distribution, okay? And then when you go to the next iteration, you have a forward SDE, which is initialized the distribution of the data, and its drift is obtained by time reversing the previous SDE. Okay, so you have like, this is basically the recursion you have between this drift, and each time you have the score of the previous SDE that pops up. And you can do the same thing with score matching and so on and so forth, and you can approximate that numerically. Okay, so this is an example here, a simple example where we have two-dimensional data distribution. We don't diffuse them enough, okay? So that basically we know that standard denoising diffusion model wouldn't work. So if you were just do one iteration of diffusion Schrodinger Bridge, the algorithm implementing the Schrodinger Bridge before, then it would correspond to do denoising diffusion model on your very far from basically where you want to be. The data distribution is normal because you haven't diffused enough. So one iteration of IPF is not going to be enough. But if you iterate here, you see about 20 iterations, you are able to reconstruct the data distribution. Okay, so that's diffusion Schrodinger Bridge. We have it for Celebi, okay, as well. So that was 2021 results. It's not that great. It's get better. But basically, you can simulate also image. On here, it's like, it's about 3,000 dimensions. Not that impressive for people. Basically, been working recently on diffusion model. We are much higher quality result available, but we did that with very limited computing resource at the university. So it's not that bad for that. Okay, so what you can do also, which I didn't say, is that obviously this Schrodinger Bridge thing, the good thing is that it doesn't require you to go from distribution of the data to Gaussian distribution. Essentially, you can go between any two distributions, live on the same space, as long as you can sample from those two distributions. So for example, you can go from basically, this is here, EMNIST. This is a database like EMNIST, but for basically characters, letters, to MNIST. Okay, so you can basically transport between any empirical distribution, because you never have this concept that basically you need to diffuse, you need a forward dynamic that diffuse to a kind of easy, kind of well-known target distribution, like a Gaussian. Okay. Okay, now, just to conclude, in the 5 minutes I have left, why I got interested in that is because obviously I'm not particularly per se interested in sampling, doing unconditional generation, like we say in generative modeling, but you like to do conditional generation. So particular, so what you have is that you given some kind of it on what you want to do, you'd like to sample from the posterior distribution of so it turns out that there's a way to do that with with actually generative models is actually quite elegant. Okay, so the most obvious thing you could think of doing is say, okay, I have access to the likelihood, okay, that have been used to noise my data, and then with this kind of generative model, I can sample from some kind of data-driven prior. So I could try to combine that in some kind of MC algorithm. People have done that. It's super expensive and doesn't work that well because you still have to do MC in extremely high dimensional space, and you don't want to do that. Okay, so we're not going to do that. So we like to do directly a Schrodinger bridge. For example, that would be able to take me from, I go from the posterior to the Gaussian, and then by learning some kind of time reversal, I'll be able to kind of, obtain sample from the posterior. That could be maybe the thing you want to do, but obviously the algorithm I've described previously doesn't work because the algorithm I required previously, it requires you, when you solve the Schrodinger bridge, to be able to sample from the terminal distribution, initial time or the terminal time. Okay, so I cannot, because the posterior distribution is what I want to sample from. Okay, so that doesn't work actually. You cannot do that. Okay, doesn't matter. You can go around that. So what you're going to do essentially, you're going to solve a transport problem on extended space between like state space, image space, like clean image space, so you think of it, and then some kind of Y, the space of Y where your corrupt observation lives. Okay, so you do a transport between basically those distribution. So the first thing is the kind you see the joint distribution of X and Y under your Bayesian model, and then the kind of simple target distribution you want to sample from, okay, where it's going to be, say, the Gaussian, times the marginal distribution of y under this Bayesian model. Okay, I can easily sample from that. I take a sample from a database and I just correct it and I'm done basically. Okay. Now it's easy and that's a trick that's been used many times in the literature. I attribute it to Youssef Marzouk, but I think other people did it also elsewhere. That basically once you've learned the transport between this kind of two joint distribution, it's very easy to extract from that a transport to sample from any posterior distribution as given y for any y. Okay, so I'll skip the detail. You can have a look at the paper, but it's not our idea. What our contribution is to use this idea in the Schrodinger Bridge context. And what we see, actually what is equivalent to do is to solve not the intractable Schrodinger Bridge problem I had presented in the previous slide, but some kind of expected version of it over basically the marginal distribution of the data under this Bayesian model. Okay, so just skip the detail. Okay, you can use that for filtering as well. Okay, so I'll give you an example here. So this is the original image. This is what you observe. Okay, this is a corrupted version. And essentially what you do, you learn basically this kind of Schrodinger Bridge under basically image on corrupted version of the image, okay, on this space. And what you do now, every time you give me a corrupted image, I run a time reverse diffusion of a finite time horizon, and that return me a sample. Okay. And for example, here you see you have this person. The original has obviously glasses, but it's obviously not quite clear for the image. So sometimes it generates with glass, sometimes not. Okay, so I sample from this kind of posterior, approximate sample from this posterior, and think that try to do that with MCMC. This is in more than 100,000 dimensions. Okay, so that's a bit very expensive with MCMC. That's an alternative. Obviously, it's much less well understood what happened actually theoretically, but it at least scales to high dimension. Okay, so I'm going to finish with that. So this kind of denoising diffusion model is super, I think, really exciting area. Okay, so there's been a lot of work done. So at the time we work on that. We had the first theoretical result for that. I've seen we extended that to discrete space on Riemannian manifold. There's been other contribution as well, independent contribution. We've shown also how to link this kind of generative modeling, ideas to optimal transport, and in particular to the Schrodinger Bridge problem. Ever since, there's been a flurry of papers where people also have developed new kind of transport mechanism so as to actually solve generative modeling problem that do not rely on diffusion. Actually, they completely bypass the diffusion. Basically, you can, whenever you have this type of algorithm, okay, to do unconditional generation, it's very easy to adapt them to do posterior simulation, approximate posterior simulation. I think what is of interest for a lot of people, maybe a statistician sitting in this audience. Okay, so if you're interested, these are basically the kind of two, I think, key papers in the area that basically started the whole actually craziness, like this field. And these are some of our contributions in the domain. Thank you.